Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, I'm going to use as an opportunity a video I did recently on a Casimir-based cosmology, where the author in the article that I presented actually talked about the famous, and I even said infamous, sum over all natural integers would be kind of equal to minus 1/12. And this was used in a particular derivation. And in fact, what I intend to do is, after having done that, then I'm going to look at basically using that particular value in a toy model that was presented in the paper. And I'm going to go a bit more in details on how to get a sort of toy model of the Casimir effect. Okay, so how do you get attraction between, let's say, plates or something, at least in a naive way, by looking at so-called, zero mode fluctuations or vacuum fluctuations and so on. That being said, that's not the point of today. Today is a mathematical point to realize a little bit what it is that we are doing when we assign the value minus 1/12 to the infinite sum of all integers. Okay, so before we actually start, I'm going to rely on some formulas. Most of these formulas can be kind of easily derived on your own. If you want me to actually have a go at deriving them, then I will. But basically, I'm going to use this as a starting point, and then we are going to see what it is that we want to do. So, first of all, there are two main formulas I'm going to use. The first one is the infinite sum of a geometric series, okay, but where I start the series from 1 instead of from 0. Now, in that case, actually, that's the same as starting the series from 1, except that I multiply by the geometric factor, or the geometric progression factor, which is a here. And basically that's just giving me a over 1 minus a. Okay, so that's basically this particular sum. I'm going to use that. And this is valid if the absolute value of a is less than 1. Okay, it can't be equal to 1, it's less than 1. There's a problem, as you can see here, if it's equal to 1. Okay, so that's the first one. The second one is basically the binomial formula, which usually is for any a plus b to the power n, but here I'm simply going to use, instead of a plus b, 1 plus epsilon to the power m, okay? And this is the expression of the binomial formula, which I believe is actually due to Newton, what we are going to use it for is essentially we are going to truncate it at some point, and also we are going to assume, which is not necessarily kind of the case, that strangely enough, m can we can somehow substitute m with a negative number. So then the question we want to ask is, how can we assign a finite value to that particular sum? So, of course, the very first thing to say, and that's really important, is that this particular sum, 1 plus 2 plus 3, etc., to infinity, is divergent. Okay? And so another way of actually putting it, because there are multiple ways for a sequence or a series to diverge. So it diverges if it's actually oscillating between minus 1 and plus 1, for example, or minus 2 plus 2. So something oscillating is not convergent, so it's divergent. But here, essentially, the result is equal to plus infinity. Okay? So if there is any kind of limit you can assume for it, the limit is going to be plus infinity. So it's divergent in that sense. Okay? And that's fairly easy to see. If we just increase this thing and we calculate the so-called partial sums, we see that this sum simply grow and grow and grow and never actually seem to curb and then basically kind of saturate to some fixed value, which is normal because we always increase by the same amount. Okay, so that's basically divergent period. Okay, so we can't assign any, we can't basically, like this actual thing is equal to plus infinity period. Now the question we want to ask is whether there is any way to assign, so that's an assignment, assign a value to it nevertheless, okay? And how do we do that? And so what we are going to look at is basically the following. So we note that the sum for n is equal to 1 plus infinity of n is equal to, so that's going to be equal to the limit when alpha tends to 0 of the sum for n ranging from 1 to plus infinity, and then n exponential minus alpha n. Okay, so here we see that there is already a first possible approach we are trying out here. And this approach is basically to look at a regularized expression. So this expression actually converges as long as alpha is positive. So if alpha is positive, then this particular expression has to converge because of the very, very fast decay of exponential minus alpha n, okay, with n. Okay, so this thing is going to converge, and then something that we may try out is what happens when alpha tends to 0. Do we get something that is going to be finite? Do we get something else? In any case, what can we learn from it? So that's what we are going to do here. Now, one of the things, and that's a very important trick, which I recommend you you look carefully and then try to use yourself in various situations, that when you've got a form like that, you can realize that this quantity here is equal to minus the derivative with respect to alpha of basically what I'm going to call, well, to the sum n from 1 to plus infinity exponential minus alpha n. Okay, so that's, you know, that should be kind of straightforward. And I'm going to call this expression here S of alpha. So we see that there are multiple things to be looked at here. So S of alpha is equal to the sum, and I'm going to rewrite this as follows, is equal to the sum for n to plus infinity exponential minus alpha to the power n. Okay, and what we see is basically that this has exactly the same form as the one we've seen earlier. Okay, so it has this form of the sum of a to the power n. Therefore, I can write that this is equal to exponential minus alpha divided by 1 minus exponential minus alpha. Otherwise, I can write this as 1 divided by exponential alpha minus 1. Okay, so that's what I can write, and I hope you can still see. I know that there is some reflections coming from the lights in the ceiling, but I hope you can still see. So then what I'm going to do is I'm going to differentiate. Okay, so I'm looking at minus ds d alpha is going to be equal to, and so that's exponential alpha divided by exponential alpha minus 1 squared, right? So basically that's what I have. Now, what I want is basically, I want to basically try to take the limit when alpha tends to 0 here. But the thing that I need to start doing, and in fact I should have put it somewhere, is basically I need to start expanding things in powers of alpha, because alpha is small. So I need to try to expand things and then look at how it varies in terms of alpha. So what I'm going to use here is the formula for exponential of x is equal to the sum for n 0 to plus infinity, x to the n, and then n factorial. And what I'm going to do here, and I'm going initially to stop at the power 3 in alpha, and you're going to see why I'm doing this. So we are going to have here 1 plus alpha squared over 2 plus alpha cubed over 3 factorial. And then in principle I've got some other terms. And then divided by, and I'm going to get the same thing here, but I've got a -1. So the only thing that I'm going to get is actually alpha plus alpha squared over 2 alpha 3 factorial squared. Now I'm going to write this in a different manner now. I'm going to write this as 1 plus alpha squared over 2 plus alpha 3 over 3. And then here, I'm going to write it as alpha plus alpha squared over 2 alpha cubed over 3 factorial to the power -2. Okay? Now, what I want to do afterwards is basically use that particular expression. So this expression again works for integers, and I'm going to admit an extension of this formula afterwards. Okay? So now what I want to do is basically factorize here by alpha to obtain an expression which is in 1 plus something. Okay? So if I factorize by alpha and alpha goes outside of the parentheses, I need to put it to the -2. So I've got alpha to the power -2, 1 plus alpha. That's factorial here. And then I've got here 1 plus alpha over 2 plus alpha squared over 3 factorial plus etc. and to the power -2. Okay, so once I'm here, then what I need to do is basically I'm going to call whatever this stuff is, I'm going to call it epsilon. Okay? Then I'm going to say that from the formula I've got here, if I truncate it, I'm going to get the following. So 1 plus epsilon to the power m is approximately equal to 1 plus m to the epsilon times epsilon plus m times m minus 1 divided by 2 epsilon squared. So far this is a fair truncation with regards to the binomial expression, but now what I'm going to do is allow myself to actually have the value m here, the m, not the n, the m value to actually be negative. And so if I've got, so that's again something I'm allowing myself. There is another way to show it. I think it's a bit easier if we start from something that is true for integers, and I somehow extend it to something else. So that's going to give you 1 plus epsilon to the power -2 is approximately equal to 1 minus 2 epsilon, and then plus -2 times -3 divided by 2 epsilon squared. Okay? So that's what I have. Now what I need to do, so that's where we are, okay? And I'm going to try to get basically a simplification of that expression. So what we get here, first I need to evaluate epsilon squared. So remember I said epsilon squared is equal to, so that's alpha over 2 plus alpha squared over 3 factorial, and that's squared. So basically this is, again, I'm going to approximate, and that's alpha squared over 4, And now, actually, I don't care anymore. I'm not going to keep using terms of order 3. I'm just going to say that the order of magnitude of what remains is of order 3. Okay? So it's just so that I don't have to carry out these things that I know are not going to matter. So now I've got this particular expression, and I need to be careful, of course, here, because I see that I'm going to have a minus 2 times minus 3 divided by 2, so it's basically 3. So this term is going to be 3 over 4 times alpha squared. Okay? So now I'm trying to put all of that together, so I'm going to get that minus ds d alpha is approximately equal to alpha to the minus 2. So by the way, this was approximation here. Then I'm going to keep only terms to the second order. So I'm writing simply O of alpha 3, so that's the order of magnitude. And then here I need to be careful, so that's 1 minus 2 epsilon. So basically I just keep the epsilon, but I multiply by minus 2. So that's minus alpha over 3. So minus alpha over 3. And then I have plus what we said earlier, 3 over 4 alpha squared. So just trying to see that I'm not messing around. Yes, I'm messing around. This is a squared here as well. And this thing here is this term, 3/4 of alpha squared, so plus O of alpha cubed. Okay? Now, this term can be lumped together, so we are going to get, I need to multiply all of that by 4, so I've got minus 4 here, and then here I'm going to get plus 9 over 12. So this thing here, overall, is going to give us plus 5 over 4, and then alpha squared. So then what I need to do is simply multiply these two expressions together, and I'm almost done. So we are going to get alpha to the minus 2. Now, what I'm going to do is multiply from the left to the right. So what I'm doing is that I multiply 1 with 1, plus 1 minus alpha, plus 1 minus alpha 3, etc. So first I'm doing this to say that I'm taking care of the 1. Okay? So I'm going to get 1 minus alpha, and then plus 5/4 of alpha squared. And then for now, I'm keeping only the terms of order 2. So I stop there. And next, I move on to the second term here. So this one. So I've got alpha times 1, so that's plus alpha. And then alpha minus alpha, so that's minus alpha squared. And then plus, minus alpha squared, so that was here. And then again, I would have a term of order 3, which I discard for the time being. And then I've got plus alpha squared over 2. And then basically that's it. I would have some other terms here of order 3. Okay? So now what we need to do is simply add up together. So first of all, we see that this term minus alpha actually cancels with plus alpha. So they disappear. There is no term in alpha. Next, what I notice is that minus alpha here is going to be minus alpha squared over 2. And here, by the way, I apologize. I messed up when I wrote my result here. This was a 12. That's 5 out of 12 here. And so now what I have is that I have minus alpha squared over 2, and then plus 5/12 alpha squared. Now I just need to multiply that by 6 to get something out of 12. So I get minus 6 alpha squared over 2 plus 5 twelfths over 2. So what I'm getting is basically alpha to the minus 2, and then 1, and then minus alpha squared over 12 plus some order alpha cubed. Okay, so that's what we have. I'm going to quickly erase on that side, and then we are going to provide a solution to our problem. Okay, so remember that what we want in the end is the following, is that we've got a sum for n ranging from 1 to plus infinity of n, and we know that this has to be the sum of the limit when alpha tends to 0 of minus ds d alpha. So that's this quantity that we've calculated here. So this is the limit when alpha tends to 0 of this quantity here. Now this quantity turns out that it is 1 divided by alpha squared, and then minus 1/12, and then plus some term here which is of order alpha, but something of order alpha means that when alpha tends to 0, this thing tends to 0, okay? So what we end up having here is that this particular strategy has not regularized the expression we want to calculate, but it has, in a sense, disentangled the infinity, so the divergent part, from the finite part. And so here, this part here is divergent, okay? And this other part here is finite. And so what we are going to say in the end, and that's what people mean, is that basically we are going to say that to plus infinity n, I can say that this is equal, and then I put here reg, so through regularization, this is equal to the sum of n from 1 to infinity, and then minus the limit when alpha tends to 0 of 1 over alpha squared. Okay? And so basically here you've got a diverging quantity. Here you've got another diverging quantity, but the difference between the two is going to give you minus 1/12. Okay, and I think that at least in my view, this particular approach does a better job at understanding what's going on. Okay, because when you use the so-called zeta regularization, you basically assign a value to zeta of -1 without necessarily understanding what's going on. Here you understand that when people write or assign a value to that, what they do is assign a value to that difference. Okay, in a consistent manner. And that makes sense then why we get a finite number. It's because we subtract an infinity from an existing infinity that so happens to get to a finite number. And basically that's the idea. That's just kind of how it works. We get this famous result that the regularized value of the sum of all integers is equal to minus 1/12. Okay, so basically that's where I'm going to stop for today. But that's essentially the idea. This thing could work in principle for other kind of diverging sequences or series. Basically this sort of exponential kind of regularization techniques where at the end you still need to subtract, like the diverging part is quite common, especially in physics. And so that's basically one of the points the author of the article I was mentioning at the beginning was referring to, we need to regularize things. We don't simply keep like the row or the bear kind of values. We need to actually regularize. Okay, so that's basically where this is coming from. At least that's one way to look at it, which personally I find more insightful than doing it, as I said earlier, via zeta regularization, because then it relies on some so-called analytic continuation of analytic functions in the complex plane. And I think this does not necessarily talk to everyone, nor does it kind of show that it can be viewed in that particular fashion. Okay, so in a further video, we'll see how we can apply that to basically the Casimir interaction.